Welcome to today's lecture. Today we're going to talk about architecture patterns, which is actually the starting point for the architecture design package. So last 2 weeks we spent on trying to figure out why we do architecture design at all, and then last week we spent on architecture documentation with views and also various ways of documenting the concerns for specific stakeholders, etc. But now we will move forward and start talking more about the actual process of designing the systems, and the basic problem is as we all know, that we have some kind of situation where we have an idea or a vision for a system, and that idea consists of some functionality and some quality that some users, various types of users, will face. And to do that, we have some kind of material, we have some tools to do the work, and our task now is to devise some sort of solution at a high level where we make decisions about the system as a whole and leave the details for later. So again, we can return to this house analogy that we talked a little bit about last time, where we had different views. We had for the plumber, for the electrician, for the floor plans, for the carpenters, and so on. We can use the same analogy here to explain a little bit more what we mean by this architecture design. Well, if you're going to build a house using a wooden frame, or if it's a concrete frame, well, or if it's a steel frame, that's the material. Based on the type of material you choose, you will have to use different types of tools. And you also, to some extent, limit yourself what you can do. If you choose wood, it will be difficult to build a skyscraper. But if you use concrete, well, you can build something that is quite high, but not as high as if you choose steel. So the same holds for our systems. If we choose certain technologies, certain approaches, we can build certain systems better compared to if we choose another technology. We also leave the details for later. When we construct a house, we don't have to talk about the colors or the wallpapers or where to place furniture. We can leave that for later. We can have an interior designer to help us with that. In the same way, when we design our systems, if we decompose our systems into subsystems, we can have some designers that are responsible for designing the interior of that component, so that the interior of that component satisfies the interfaces that define what that component should satisfy in terms of functionality and in terms of quality. So how do we do this? How do you design things? Well, we talked about this last week or the week before or both. Typically, we base our designs on our previous experience. That's the starting point. And to some extent, that's fine, because design is a creative exercise, and you know, Back in the good old days when you had craftsmen, they had a system with a craftsman and some apprentices that learned the trade from this craftsman. So the craftsmen, they learned working with something for a long period of time and then sharing that knowledge with young people, and that was how we learned. But then at some point, well, we had to introduce more rigid transfer of knowledge than this apprentice system. So we started to talk about engineering. And the first engineers, they built typically forts, fortifications for military. And that's why they are called civil engineers in Sweden, civilians. So they were not military, they were civilians, but they worked with this. And engineering and craftsmanship are different when it comes to one thing, and that is that the craftsmen rely upon their personal previous knowledge or knowledge that was transferred or given to them when they were apprentices. But an engineer does not just rely on what has been tested, what has been tried. They can also do things and do predictable things, which means that you don't have to try to see if your skyscraper holds. You can actually calculate. You can use the right material, use the right dimensions to come up with a guarantee that your design will work. A craftsman, they guess to some extent, but they can be very experienced, so their guessing is really good, sometimes much, much better than an engineer. But at some point, well, the engineering approach is better, and that is when it comes to the unknown. Because we don't necessarily have to try out the unknown. We can actually come up with a model which is good enough so that we can predict the outcome of a design. So when it comes to software design, what we have to deal with then is, of course, a set of requirements. A set of requirements that we find in binders full with papers or in some online system or somewhere, somehow, on sticky notes or whatever. But our first task now is to come up with some decomposition. And last week you guys worked a lot on a first level decomposition for the functional requirements, more or less allocating responsibilities to subsystems so that the most critical or most important core functionality of the system found support. Someone were responsible for this in the whole system. How did you do that? How did you do that? Well, I think that what you did was that you, to some extent, used knowledge. And you devised some architecture, and you had a look at this architecture, and you started to reason about it. Is this good enough? Have I allocated responsibilities that are required? Are there any interfaces that are missing? Are there any parts of the interfaces that are that are missing and must be supported? You started to talk to yourself and ask yourself a lot of questions. And then you went back, you revisited your architecture, you refined it, you modified it, until you felt that, hey, now this first level decomposition supports the requirements as specified in the requirement specification. So you use this analytical framework, and the analytical framework is actually what distinguishes an engineer from the craftsman. The craftsman's analytical framework is solely based on their experience, what they know or what others have communicated to them as their experience. They don't really have the tools to predict what has not been done before. But as an engineer, your analytical framework consists of more than just knowledge. But still, knowledge is important, and knowledge can come in many formats, not just your own experience. You can also get knowledge from what others have done in a similar way as this apprentice. But when you read a book, what do you do? Well, you read about someone else's knowledge. When you look at an existing system, what do? Well, you learn from others. You get knowledge from others. And some people, they have produced a mathematical model that you can use to evaluate some property. For instance, a performance model. So what can you do with that performance model? Well, you can take that knowledge of how to create a performance model, and you can take a candidate architecture, and you can evaluate that candidate architecture with respect to performance by creating a performance model. So with this performance model, you can predict the performance without having to invest the time in developing the system and then measure the performance. A craftsman would say that, based on my previous knowledge, we should do this. However, that can be wrong, because there could be something different that you don't notice. But if you create a mathematically based performance model, you can say something which is not based on your previous knowledge. So is this fail-safe? Of course not, because these models are abstractions and based on what people have experienced, but still, they are typically stronger than a single individual. So what you need to find now is, of course, this little balance. Balance between degree of formality and usefulness. So for the important things, you use more formal models. Sometimes that's a requirement, even. If you're building a system that might cause harm or injury, well, the degree of formality in your reasoning, you have to come up with solid arguments and even evidence that the claims you make about the system are true. So, at the architectural level, any system, every system has an architecture. So all systems that have been built has an architecture. And that means that we have a lot of knowledge from the systems we built. But now we need to package that knowledge in some kind of attractive, reusable format. And if you go through the literature in software architecture, you will find 3 types of architectural knowledge. 3 types of reusable architecture knowledge. Next lecture we will spend on tactics. Tactics are proven solutions to specific problems. Like, we would like this type of behavior in our system, or we would like that type of behavior in our system. Well, then you can use a tactic. But it's not about functionality, it's about how to achieve quality. So there are tactics for authentication, there are tactics for detecting if something has failed, there are tactics for recovering from these failures, there are tactics for many, if not all, of the concerns you can imagine for a single system. So next time we will look at some of these tactics and how to use them. But the focus of today's lecture is patterns. We'll come back to that. But then we also have reference architectures. And a reference architecture is typically a template for a solution, where you see a combination of tactics and patterns combined into a template for a complete system. So if you look at, for instance, a reference architecture for a standard web application stack, you can fill in different, you can see different patterns applied, you can see different tactics applied. So it is something that takes the knowledge one step further towards a specific application. So if you imagine the level of generality, patterns are really general. They can be applicable in many different situations. Tactics are much more specific. So you can actually apply patterns to tactics to get them, to shape them differently. But it's difficult to apply tactics to patterns. You see? And when it comes to the reference architectures, they're down here, because then you're mixing patterns and tactics to get a template which is kind of quite close to what an actual application looks like. So I will say a few words about reference architectures at the end just to illustrate that, but we focus on patterns today. So a recurring structure or some structure and behavior that addresses one or more concerns. And this is not something that is unique to the software architecture level of design. It's in fact something that we see at all levels. We know that our software systems, they are hierarchical and they exist in a context which is a system, and that context is in a context which is a system. So, and it means that you can see patterns at all levels. But we focus on software patterns, and this is a general solution to a common problem, but it's packaged in a way that it's quite easy to find, but also use. But it's not a tool that fits directly. You need to massage it a bit to fit your specific context. And you see patterns at all levels. Design patterns, you probably heard about design patterns. Paradigm-specific patterns, recurring solutions. So if you have a design problem, say that it's object-oriented design, well, then there are object-oriented design patterns, so they are connected to a paradigm. And there are some very famous design patterns. There are some creational, there are some structural and some behavioral patterns that you find in the book of the Gang of Four. Then we have architecture patterns. Also focusing on organizing components in a smart way. But even one level up, we have patterns. How do you organize your enterprise? How do you organize your organization? And that's important because if you're in a large enterprise, it's a challenge to manage all the people. And it's the challenge to organize all the software systems that should support this people in fulfilling the goals of the business processes you have. And then, of course, we have all the way down at the idiom level. Idioms are typically tied to a specific programming language. There are certain things that you do in a language like JavaScript. There are certain ways of doing things that is specific to that language. And there are certain ways of doing things that are specific to Java, and some that are specific to C++, etc. So in this picture here, at the top here, what you have is a much more general pattern than the items at the bottom. Okay, so when you read literature, there is a mix of concepts. When this was introduced, the concept of a pattern was introduced in the early 1990s. It was just about the same time as people started to talk about design patterns in software. So people didn't want to call it design patterns or architectural patterns at the time. Instead, they called it architectural style. But I would say that that's not the only reason, but in the beginning, people were more geared towards it was not a reference architecture, but they were more descriptive when it came to the type of component that should be included in the architecture, the type of subsystem that should be, and also the type of connection between the subsystems. As you will see later today, there is a blending where you blend not just how you organize the subsystems, but also the characteristics of the subsystems. They are not just subsystems with interfaces, they are subsystems of a special kind with a special or dedicated responsibility. So there's a little bit of mixing in things, but over the years it has evolved towards more of a traditional software pattern approach, as you will see. So an architectural pattern, structural organization schema for your software systems. It provides a set of predefined subsystems, but what you should think of here is predefined in the sense the responsibility. They are responsible for something. And that something can be a type of behavior, a type of connection, something like that. But it's not about how this is achieved. And then there's also guidelines for how to combine these in a way that you achieve what you're looking for by applying this pattern. So this is not too far from the software pattern definition or design pattern definition. It's super close, really. However, what you will see is that the patterns are not generally applicable. It depends on which concern you're interested in. So what you would like to communicate, what you would like to describe, to that extent, to some extent, that decides what type of patterns you can use. And that means that all these architecture patterns, not always useful, however, by reusing the same patterns or calling the same type of structures with the same type of responsibilities with a name, that defines a language that is very useful. If I say client-server, which is an architectural pattern, I believe that most of you immediately understands the type of system we're going to talk about. But if I say a pipe filter architecture pattern, suddenly, what is that? But when you know what a pipe filter architecture is, it will be as clear as a client server. So we will establish a design language that architects can use when they design the architectures. You don't need to explain all the details because that is implicit. It comes from the label. So you get a language, but as I said before, you need to combine them, connect them to the views, I should say. Because not all patterns are interesting in all views. Think about the functionality view for a user. What type of patterns are interesting there? Well, that's not really about the architecture itself. It's more about the functionality the architecture should provide. But if you start to talk about that, yeah, you will get a client that you can install with this functionality, well, then you can use a client-server pattern. So sometimes these patterns are useful, at other times they're not. But as you will see later today, there will be specific patterns that are useful when you want to communicate specific aspects of your architecture. So from a documentation perspective, as I said, it's a language for designers. And this is also recognized in the standard. Architecture patterns is an entity that this ISO 42010 recognizes as a first-class element. You should use patterns when you document your architecture. And what you see here is that in your viewpoint, they will provide a set of patterns, specific patterns suitable for that view, or for views created from that viewpoint, I should say. So when you instantiate your architectural view, you will instantiate the patterns. You will contextualize the patterns. So, as you see here in architecting, and this is a reasoning example. Over at this end here, over at this end here, what you have is requirements. You have a set of requirements that should be considered when you create your architecture. And as you will see over at this end here, is a view. And you will create views using tactics and patterns. And what happens here is that, well, you will get an architecture view. You can have a performance view. You can have a functionality view. You can have something, and that can be evaluated using this quality attribute model or evaluation framework. So patterns help us when we document, when we describe our views. So if you look at some connections between patterns and views, it's kind of clear that there is some connection. Sorry for that. It's like when you have machines that don't allow you to do anything or everything. But one of the challenges, you remember in the greenhouse example, we had Mary. She was like the main architect. One of her key responsibilities is to manage the complexity. We also have a developer involved in this project, and his responsibility is also, of course, to manage the complexity when it comes to the implementation. So there will be lots of code to organize for him, and two different views. In fact, you can have a system view where you need to manage the complexity. You can have a code view where you need to manage the complexity. And the question is, like, how can you do that? Well, and as you will see, that one very popular way of managing complexity is to layer your architecture. Create layers. And those layers can be logical abstractions. So you can create a layer which is a logical abstraction, but you can also have code organized in layers. Code organized in layers. Yeah, that's a nice thing to have, because if you have a layer at that level of abstraction, you can focus on that level of abstraction and what that level of abstraction provides and how it provides it. You don't have to consider layers beneath. You can just assume they work. Okay, what's very popular these days is applications that deal with huge data volumes. So you have streams of data. How can you, or big chunks of data, or large volumes of data, how can you deal with them? Well, in principle, there are, on this slide here, there are two examples. You can deal with them in batches, or you can use this pipe and filter architecture. Two options. You're now the architect. What do? You have a look at the batch sequential, and you have a look at the pipes and filters. And you try to figure out, for my high volume, data intensive application, batch sequential is the best one. Whereas for some other application, I would favor pipes and filters. So you assess the situation, you evaluate the options, you pick the one that meets the current goal criteria the best. And we can move on. We can look at more examples. We can look at, for instance, user interaction. That's kind of interesting, yeah? How you organize your architecture actually promotes or enables our designers and developers to implement certain concerns. Say that you have for your data intensive application here, you have stakeholders that have different interest in which data they are presented with. So they would like one of these nice looking dashboards where they can pick and choose whatever data is made visible to them. Okay. Two options, or in this case, three. I believe that you guys don't know what C2 is, but that's an architecture pattern which can be quite a good decision here. But a model view controller, I believe most of you have heard about this. Presentation abstraction control. Kind of similar, but not exactly the same. Usually I get someone who gets really upset, and then they point at some papers that were saying that this is exactly the same. And yeah, could be, but we would like to keep them separate. At least the guys who described them initially. Pope, who came up with the model view controller in 1976, I think. I have the original paper there from the Smalltalk community, and he had no idea about how popular this would be 30 years later. And then someone comes up with a little tweak and call it presentation abstraction control, and it's different, yeah, a little bit here and there. But the properties are somewhat different. And of course, when it comes to component interaction, that is how we define the communication between the subsystems in our whole system. Well, then we have a plethora of options. We have synchronous or asynchronous communication. We can have a message invocation explicitly calling a method, or we can have an implicit one. We can organize the system as a client and a server talking to each other. We can have a peer-to-peer, and we can have publish-subscribe. There are various ways of addressing different aspects of how components or subsystems in our system interact. And then, of course, there are the interactions here. That is more when you have a decentralized system. And that's really popular these days. Someone would say, but client-server is also about distribution. No, not necessarily. It only says that you take the functionality and decompose it into a client and a server. Doesn't necessarily say that you need to distribute them on different computing devices. But if you use remote procedure calls or a broker, that means at least that they run in different memory spaces. And they could be useful to describe also decentralized distributed computing systems. And with these patterns for different views, different aspects, concerns your systems, well, first lecture I showed you this example. And this is actually the simplest example I know of where you can actually see that, we will get some properties that are enabled by your pattern and some that are inhibited. It's more difficult to achieve scalability if you have a client-server approach. So what would you say is what can you do if you would like to ensure scalability with a client-server? There are lots of client-server systems around. I believe that your web browsers and web servers are the most common ones. So you have clients and you have servers at that end. What can you do to guarantee that the more clients you have on this side, that the server side is able to respond timely to their requests? What can you do? Any ideas? Sorry?
Clustering.
Clustering, which means more or less that you have a farm of servers at this end, and you activate and deactivate them based on, well, the number of current active clients and the number of requests. So you have some kind of load balancing mechanism. Yes. That's one example. So what you can see here is that if you choose the client server, but would like to guarantee scalability, you have to do your homework. You have to address that in a different way. You don't get that for free. Same with reliability. There is a single point of failure here. And if that single point fails, no client can access the server side. Clustering is again a possible answer here. You can have a hot standby, you can have a server farm that, well, takes over that. But then you have to think about, what about stateless? How do you deal with state if you have session things like that? A little bit more complicated, but doable. So architecture patterns enable certain qualities, but they also make them, some of them, a little bit more challenging to achieve. So think about that. So it's time for the short break, so let's do 10 minutes from now. So it's time to continue. What we talked about before the break was more or less introduction to patterns. But let's look more into the application of the patterns in this second part. This is not something where a PowerPoint is really useful, but I will try to do my best. There will be a lot of boxes and simplified models, etc. But the message here is that you should learn the patterns. You should learn the upsides and the downsides with the patterns. And then, with that knowledge, you can choose the patterns and you can apply them to your design problem. And as any other language, programming language or natural language, you need to practice. You need to do things that are good and also learn from failures. But I will try to show you some of the underlying ideas for how to apply these patterns. And we start with well, quality concern, because that's where it all starts. So here you have another ISO standard, and it's a way to organize quality. And there are a couple of boxes here, but we can focus on the maintainability. Maintainability, what is that? Well, according to this standard, it's about analyzability. Well, if you want to maintain something, it's important that you understand what it is. And something that is easy or easier to analyze is typically easier to understand compared to something that is not. So, what else do we have? Well, we have a property called changeability. It's the changeability property that says something about how difficult or easy it is to change, how flexible is this system or this subsystem. Testability, how easy is it to test? If it's easy to test, it's easier to maintain compared to something that is not easy to test, because you need to invest more effort into testing for a system, subsystem with lower testability. So, if you look at these concerns, these qualities then, and the properties you strive for, the ones that are in these boxes, well, what you can say is that, from the patterns you will find support in achieving these, some of these. But you will also find that some patterns work in the opposite direction. So you cannot really do architecture design without a full picture of the quality concerns, the quality attributes, the quality requirements for your system. But this is the working example, and you remember that Mary, she was the main architect for the system. One of her challenges here was to manage the complexity of the system, come up with some nice structure that could reduce the complexity of the functionality, and also to some extent some of the quality in the system. And how can we do that? You remember the list of example patterns we had on 2 slides before the break? So, were there any patterns that could be used to reduce complexity that you remember? This is like the goldfish test, you know. When you circle the glass bowl here, the world is always new. So this is a check. Remember? Well, to master complexity, we could use layered systems. Because where do you find the devil? In the details. Okay? The more detail, the more complexity. So, what we're talking about here is something that can be used to reduce complexity. But because what we do is that we create abstractions, layers, that hides details about how certain things are achieved. So at the top here, we have a layer that uses a layer below, that uses a layer below, until we have a first layer, layer 1. And this layer here, this one here, uses, I should draw it there, uses services of behavior provided by this one. And then it goes on like that in turn. So what we have up here is an abstraction that hides all the details beneath in the layer, or all the details of the layers beneath. So this is an example, and you remember from maintainability that changeability was a key thing here, right? So how do you get changeability from this? Can any one of you imagine or come up with an example of a layered implementation? Yeah, the assignment, yeah. But from the real world, from the not the assignment world. A network, sure, that's a very good example. And what do you have if you think about your phone, or if you think about your computer? Well, what do you have here? In this phone, you have some software running, and in this computer here, we have some software running. And it can, in fact, be the same software, except for one thing. One layer. So if I would like to change the networking stack that works on my cell phone so that it works on this computer, in principle, it's a simplification. I have to replace the network device driver. In principle. So that's an example of the layers and how they work. And that changeability will actually also give us portability. So since we can pull one layer out and replace it with another, if I would like to port my network stack to another context for some other hardware, I have to provide a device driver for that network device. So we have maintainability because it's kind of easy to change. if some guy comes up with the brilliant idea that we should move this system from A to B, well, maybe we just have to replace layer 1 that interacts, which is the lowest level, which interacts with the underlying system. We don't need to replace everything, or we don't need to go in and check if everything works. Because since we have this nice layered separation, we trust that the layer beneath will work if we replace it with something that implements the same interface. Because that's the key of the layered pattern, that you have stable interfaces and that a layer only relies directly on the layer directly beneath. But you get a problem, of course, because people tend to work around these rules and shortcut and say, hey, I don't want to go through the entire stack of layers here because it's costly. Cost me in terms of performance. There are too many method invocations here before I get to layer 1. And I know what I want to do, so I go directly to layer 1. Suddenly, we have a problem, because if someone wants to move this to a new environment, well, we have a dependency directly to layer 1. And changeability is long gone. Portability is also long gone. So as long as you stick to the rules, it works. But if you don't, if you violate the rules, it's not the pattern anymore. So don't expect the positive things you get, or would have. Question? Yes?
What's the difference between external and internal quality?
So the question here is the difference between internal and external. And the definition that is most common is that something that can be experienced by the user, or something which is external to the system. That could also be another user, another system. That is an external quality. Whereas an internal quality is something that can be experienced by the developers of that system. So for instance, maintainability, that is not an external quality, because you don't sit at home and use a system and think about, okay, this was not very maintainable. But you can think about, this guy eats up my resources. Or this is a slow one. So that's the distinction between internal and external qualities. So, well, that was an example of portability, but we got this OSI example. What is the OSI? Ever heard of OSI? Yeah, good. Have you ever seen an implementation of the OSI stack? Nah, not really. But you know what this is? This is actually an example of a reference architecture. It's a pattern which is also a reference architecture. Because the definition of a reference architecture is that it has to be implemented. It's a template. And it can be implemented in many different ways. So, in principle, the TCP/IP stack, network stack, is an example. It's an implementation. It's not a one-to-one mapping of this, but you will find elements of the different layers matched by components, subsystems in the TCP/IP stack. But as you see here, there are lots of indirections for an interaction that logically takes place here to go all the way down the stack and all the way up, passing all the layers. Much easier if we can do something here, of course, if we consider performance. Because the advantages here is the maintainability, the support for evolution, reuse, we have standardization, etc., etc. You can get a hardware device from any vendor as long as they provide a device driver, and you can make it work with your operating system. If you have a cell phone, non-Apple, I would say, well, what they do is, of course, that they come up with the hardware and they provide device-specific drivers. Some of them are so generic that they don't even have to do that. They can just rely on the drivers provided by Google if it's Android. Downside, the negative, performance, as I said. And if you change behavior, if it's not supported, you will like get a ripple effect down the layers. But in general, this is I would say the most common model used for complex systems to manage complexity. And it's abstraction. It's the good old abstraction friend that we use again. We create an abstraction that uses other abstractions below. We remove knowledge, or I shouldn't say knowledge, we remove information that we don't need, and we can focus on what we need to know. Here are some examples of where you can find usage of layers. Operating systems is a common one. JVM, the Java virtual machine, that's another example. If we look at this one, suddenly we have to talk about efficiency, reliability, portability. We can think about views a view that discusses all three aspects here of a certain quality or a certain functionality in our system. And what you have to think about now is really, well, what is it that can enable reliability? What is it that can enable efficiency or has an effect on efficiency? What is it that can enable portability? Well, if you think about the subsystems themselves, yeah, if a subsystem fails, that has to do with reliability. If a subsystem is inefficient, that also has to do with the reliability, with efficiency. And then the portability we saw from the layered example. But what's really interesting is that if you look at what really enables or inhibits these three, it's component interaction. What? Yeah. That's actually something that is decisive. How you have your subsystems communicate. That is decisive for these and other properties. Why? Well, efficiency, communication. But portability. Well, if you decouple the components, you don't have too tight coupling. You can do that with different interaction patterns. Well, the less coupling you have, the easier it will be to connect something else. Portability. And reliability. One of the properties of reliability is to reintroduce something that can replace that. And if you have, say, for instance, clustering was an example that we talked about before when we mentioned single point of failure. Well, that has an effect on how you communicate in between your subsystem. So, example patterns, we talked about client-server, a broker architecture, peer-to-peer, are alternatives. So a broker is more or less a lookup service. And you say, hey, I would like a service that can do this for me. You turn to a broker, and this broker tells you, we have a service over at this end that you may use. All other services are occupied. So a broker connects two or more parties with each other. And a peer-to-peer, we come to that to you. So client-server, we don't spend too much time on it because you've seen it. But advantages. Here are some advantages. It's not all advantages. And some of these are very specific, but it's just an example of that you actually, with a client server, you can share resources. And data and hardware can be shared in a simple way. The disadvantages on the right-hand side there are some of them we discussed before. But I tried to add a couple of concerns here that we haven't talked too much about. For instance, a client server is more work than a monolith, typically. Not necessarily, but typically. We have the problem of scalability, single point of failure. And we talked about peer-to-peer as a way to address that. What we have now is that we have something that is different because it's not fixed in the same way. We have the clustering, so to speak, built in to the pattern because the subsystems in a peer-to-peer are different than the subsystems in a client server. Okay? Because here, simplification again, all subsystems are clients and servers. And typically you find that data is replicated, which means that it exists in more than one subsystem. And that, of course, provides scalability, provides reliability. But again, let's return to this interaction pattern. Well, what you have here is a dynamic network where an open application where these peers can enter and leave the network without affecting the network as a whole. The more subsystems we have, the more reliable, the more efficient will the system be. But it has to do with the interactions here, because there must be some smart control of the interactions between the subsystems. So, what can we do to make something open? Well, coupling was something that was mentioned before. And if you look at coupling, you should avoid explicit invocation. You know, when I call you. I call you. I need your phone number. It's much better if I have a broker where I say, I call someone that can help me. And the implicit invocations provides for a much more flexible system, because I, as a client subsystem in this sense, I'm not concerned with whom provide me with a service. I'm interested in that someone provides me with a service. So it's much more flexible. It doesn't have to be A, it doesn't have to be B, it can be A or B. And if you have a broker in between, you can actually get a full support. You just send your request to the broker, provide me with this service, and the broker takes on the responsibility to look up the service, connect the two. So flexibility, you will get scalability, because the broker here can be a load balancer and say that, hey, service A is busy, we go for B. And robustness, of course, if A is down, you go for B, or C, or D. So this is an example where you have clients requesting the service. But that invocation model is driven from the requesting subsystem. But say that you have a situation where if something happens somewhere in your system, you would like something else to happen. Well, that can be managed by this client invoking a service, but it can also be the client waiting for this to happen. You see this typically in user interfaces. You don't have the system sitting idle waiting for a certain event to happen. It listens to events. And as the events occur, there is a mechanism that distributes the events to listeners, or whatever you choose to call them, subscribers to these events. And you can use that publish and subscribe model to achieve this implicit invocation. And that's a good thing, because when you subscribe to an event, you don't really know where is the publisher. You don't know when events will occur, but there is a middleware sitting in the middle, and the publisher, when an event occurs, it sends it out to the middleware, and the middleware is responsible for invoking the subscriber. So you see that this model decouples the subsystems a lot. And of course, just look at any graphical user interface framework It doesn't matter if you push a button or if you push a window or if you push a menu item or whatever. It's the same type of invocation. So these elements that subscribe to these events, they look similar in structure. Not in the internal behavior, but similar at some level. And it's the same here. So you will get the flexibility, you will get the maintainability, you will get the scalability from this model. So these are some examples, but at some level, your patterns come very close to reference architectures. We saw, for instance, for the OSI layered model, is that a reference architecture or is it a pattern? I would say it's a reference architecture based on a pattern, because it describes exactly what should be in each layer, but it's a layered architecture. When it comes to service-oriented architecture, what's that? Abstraction of a business activity with a specified outcome, should be self-contained, a black box for its consumers. It may hierarchically invoke other services. There are a set of rules there. But if it's a single pattern or if it's a couple patterns in there, I would say that you can see explicit invocation, you can see implicit invocation here. And if you think about microservices, which is yet another twist to service orientation, well, now it becomes really fuzzy here. What is it, really? And if we come back to reference architectures, a domain-specific solution template, well, as you saw in the OSI example, there were a couple of required responsibilities in the layer there. And it combined different patterns, in this case a layered pattern. But what you see on the right-hand side there, what is it? What is it? What does it say here? Target architecture using microservices. Okay. Target architecture that uses microservices. So this is a reference architecture for microservices. And if we zoom in, because I think it's a little bit difficult to see the details here, but in this case, you can see that at the top here they have an API gateway. And in that API gateway, there should be a logging service, there should be a load balancer, and they even suggest an implementation there. And then down in this part here, what does it say there? I have to check. A command bus is actually something that receives and interprets commands. And that's the interpreter pattern. And the interpreter pattern, that's a design pattern, but it's also an architecture pattern. So what you will see here, that a reference architecture combines patterns and it assigns responsibilities to the subsystems. And that's kind of, there's a fine line when it's a pattern and when it becomes a reference architecture, especially in the OSI example, because that's where they only add the responsibilities. Here it's a little bit easier, because here you can see that they mix several patterns with that together makes up the reference architecture. So, as I said, we have patterns at all levels. At the organizational level, you can talk about publish, subscribe. You can actually, with the enterprise service bus, ESB, you can connect systems within your enterprise that subscribes to events. So if you want a simple example, if you have a system that monitors another system, so you have like some operations system that monitors your cloud or whatever it is, if something breaks, you can connect using the service bus to your organization's email application and send an email. Now that's a publish-subscribe architecture at that level, connecting systems. But you can also use it at the architecture level, as we saw. And of course, the observer pattern. What is that? The observer pattern. I observe you. I subscribe to events that occur in that subject. Patterns at all levels. And now, remember, when you design, you must use the architectural knowledge. And the fact that patterns enables or inhibits different qualities. But you need to get this, start practice them to learn and see which one is better than the other in certain situations. There is no recipe that says you should always use this or that. Never. So, next lecture, we focus on tactics, which is a different approach to achieving qualities when you design your architectures. It's scheduled for Thursday, but I have to raise a red flag. Could be that I need to push it a bit. I have to travel on Thursday, and I'm not sure that I can make it to the slot. So keep your eyes open. So that's all. See you guys next time then. And now the computer decided to that we should finish too. So see you. Bye.